Hello, and welcome to part two of thermochemistry, application to heating curves and phase changes. Um, and so we're picking up where we left off with the last video. Um, the application to heating curves for MCAT is, if we remember in a heating curve, you have places where you're increasing in temperature, but you have one state of matter, or you have places where you have phase changes. Anywhere where you have a change in temperature, you can use MCAT. Can't use MCAT for phase changes because the temperature doesn't change. Heat goes into breaking or weakening the bond. Well, and what bond do we mean here? That would be the IMF, right? Because intramolecular bonds never break, if we remember. So it's going into breaking that IMF or weakening that IMF. In the case of water, that would be weakening or breaking the hydrogen bonds. Um, Cooling curves, we're only going to do an example with the heating curves, but curves would work the same way. However, the sign would just be negative for everything. You would flip the sign value for everything because heat is not released, is released and rather not absorbed. And so when energy is released, heat energy is released, that has a negative exothermic attribute. The slope of the temperature change in the lines for the places where, so if we come over to like here, like here, the slope of this line versus the slope of this line and this line in these areas, it corresponds to a smaller specific heat because it's easier to raise the temperature. So if you have a faster slope, a higher slope, then that's going to correspond to the temperature changing quicker, meaning you have to add less energy in, which means that you have a lower specific heat. And so you have to pay attention to that in some cases. And so the value for down here sometimes can be time on the x-axis, and it can also be the amount of heat you're adding. So we'll assume if it's over time, this is letting you know how you're adding heat over time at a consistent pace. And so we're going to remove these really quickly, our highlights. Okay, and so just to remember how we can label our heating curve in place number one, where we are looking down here on this part of the line. This would be only a solid. When it gets to the flattened part of the line, this is where you have melting occurring. So you would have both a solid and a liquid, and you would have a phase change. So this would be melting. And this is where your IMFs are weakening, not breaking. At part three, you would have it as only a liquid, and the temperature is increasing as you add heat because it's going into increasing the kinetic energy of the molecules. Part four, where it's flat, this would be, so we have solid, we have melting, we have liquid. This is where it's going to be a liquid and a gas at part four. And then this would be known as boiling. Evaporating. Okay, and the energy is going into breaking the bonds. And we notice here that this line here is going to always be longer than this line because part four will be longer because it takes more energy to break a bond than it does to just weaken it, or an IMF. Okay, and remember, intramolecular bonds are never broken in phase changes. And so part five here is where we just have a gas. Okay, so one of the other important values that you're going to need is going to be if you're going to do phase changes, is you need the heat of vaporization. And this can also be the heat of condensation. And this is for water. So these values here, they will change depending on what substance it is. So heat of vaporization is going to be when it goes from a liquid to a gas, or you could use this value gas to um, gas to liquid, but you would have to come up here and make the sign for it negative. When you go the opposite direction, when you're doing cooling and it's exothermic, you use the same number values, you just make the signs negative. And if we look over here, this one is the heat of fusion or melting. And then the heat of solidification of water, freezing. This would be going from a solid to a liquid. You could use it for a liquid to a solid. except for again, you would have to make a negative in the opposite direction, and this value is much less than the value over here because it takes less energy to go from a solid to a liquid than it does from a liquid to a gas. All right, so let's try a problem. There's a 6,000 gram pile of snow starting at 0 degrees Celsius. How much heat is required? So that means that this is going to have positive um, overall delta H or a positive Q value, however you want to put it. Your um, enthalpy value is going to be positive. How much heat is required to raise the temperature to 40 degrees? So our first step is always to draw a a heating curve where we show the different phase changes. So we're going to go for water, 1, 2, 3. And the two important points that we always label in this are what are our, if we're given them, our melting points and the temperature of boiling points. Those are really important because they sort of anchor everything else. So now we're going to go ahead and mark when we start. We're starting at 0 degrees. Well, everything on this line is 0 degrees. So how do we figure out where do we put it? So we have to listen that it's starting at snow. And if it's snow, that means it's solid. So that's going to start here. So we're going to increase temperature, or we're going to add heat energy, that's going to melt the snow. Once we get it all to 0 degrees Celsius liquid, then it can start to increase the temperature. And so this will be our ending point. So we have 2 segments. If we have 2 segments, then we need 2 calculations. So let's go ahead and do our first calculation. Because our first calculation, there's no temperature change for 1, that means we're going to have to use one of these constants. And in this case, we're going to use the delta H of fusion because we're melting. And this is an intrinsic property. So that means that this is a constant value. We don't have 1 gram, we have 6,000 grams. So it's going to take 6,000 times more joules to heat it up. So this is how many grams we have times 335 joules per 1 gram. Gram cancels out. We just put them into our calculator and multiply. Now, obviously, this is going to be in joules, and it's going to make a lot more sense to put this value in kilojoules because we're going to get a pretty big number here. So we're going to divide by 1,000, and we still get a really big number here. And this should make sense that it's positive because all of the values, if we're increasing, going in this direction on a heating curve, then all of our values should be positive. We should not be getting a mix of positive and negative in this case. If we're positive, everything should be positive. This is the value in kilojoules. Okay, so that's part 1. All right, so now let's do part 2. So for part 2, this is have a temperature change. So that means that we can use Q equals MCAT. So our Q is what we're solving for. Our mass is still 6,000. It's all liquefied now. C is the specific heat for water, not ice, because it's all melted now. And the change in temperature. So our final temperature is 40 minus 0. Be very careful. Look back here and make sure your temperature changes make sense because sometimes you can have multiple temperature changes that you have to account for depending on how many phase changes you have. All right, so we're going to put this in the calculator and we end up getting 4.18, 40 divided by 1,000 again. Definitely going to want to divide by 1,000. And we get 1,003 kilojoules. So the way that we get our final answer to figure out how much heat energy in total is required to do this, we have to add these 2 values together to get the total. And so our total value is going to be positive because we're adding heat energy, 301 kilojoules. All right. So for our next question, it's how much energy is required to boil 80 milliliters of water, which starts at 30 degrees C. So again, where we're going to start is with our heating curve. We're going to sketch it out. For water, we know, oops. Okay, so for water, to make these lines a little bit straighter here, we know that this is 0 and boils at 100. Go ahead and mark where we're starting. So we're starting with 30 degrees Celsius, so that would be liquid water. And again, I know that because I have my 0, my 100, And if we're boiling it, we have to raise the temperature, but it still would be liquid water at 100. We also have to take it across this line to get it all into a gas so that it's boiled away. So we have two line segments. We have 1 and we have 2. So that means we're going to need two calculations. So for calculation number 1, because the temperature is changing, we can use Q equals MCAT. Q equals mass. Since it's 80 milliliters, that's equal to 80 grams since the density of water is 1. 4.18, that is an 8. Change in temperature, if we are starting at 30 and going to 100, it's going to be 100 minus 30. Draw a minus sign. Make sure we make this 70 before we put it into the calculator. So we have 80 times 4.18 times 70, and we expect this value to be positive because we're adding energy. We're going up on the heating curve. So that should mean we have a positive value. This is endothermic. And I'm going to take my answer and divide by 1,000 to get kilojoules. So 23.4 kilojoules is my first value. All right, so my second value, 2, I can't use MCAT because there's no temperature change. Okay, this is a flat line. So we're going to have to use one of the constants. In this case, we're going to use delta H of vaporization. And again, this is a constant, and it's an intrinsic property for every 1 gram. So since we have 80 grams, it's going to take 80 times more than it does with just 1. And this value, I had to delete it from the screen because I didn't have enough room. So 80 times 2330, and these values will always be given to you. If we want to make it kilojoules, we have to divide by 1,000, and we get 186.4. This is in joules, so this will be in kilojoules because if I divide it by 1,000. And so now to get the overall value, I have to add these two values together. So we have 210 when I round it for significant digits. Okay, and that will be our total value. And we expect this to be positive because we're adding heat energy in. Okay, so we have a problem here, and this one changes a little bit because it's asking us how much energy is released. And if energy is released, we should get a negative delta H. We could also call it negative Q value. It means all of our values should be negative. I would still suggest drawing it as a heating curve because I think it makes a little bit more sense since we've seen more of those. A cooling curve is the same thing, just drawing backwards, but I always just find it easier to draw this way. So we have the value here for our melting point is 0, boiling point is 100, and we are starting here. It says how much heat is released when 25 mils of water at 90 degrees is frozen to -10. So we're starting at 90, which means we're starting with a liquid. In this case, we're going down the graph, so that's a big change here. And it's all freezing, because it says that you're going to freeze it. But we can't stop here at 0 because it wants us to go all the way to -10. So another thing that's different about this problem, so one is that we're going down, so all of our numbers are going to be negative. The other difference is that we don't just have one or two of these segments, we have 3 segments. We have 3 segments, that means we need 3 calculations. So for number 1, because the temperature is changing, we can use Q equals MC delta T. Our mass is going to be 25 because 25 milliliters is 25 grams of liquid water. C for liquid water is 4.18, the change in temperature. So our final temperature is 0. And you see, Ms. Radevi, why is the temperature not -10? And here's where you have to be careful. You're not representing the entire problem. You're representing this segment. That's what we're doing here, this segment. And this segment doesn't go all the way down to -10. That would make the graph look like this, and it doesn't. You're only going to 0 in this part. So -90. And if we do this correctly, we should get a negative Q. So Q equals, we put this in the calculator, we have 25 times 1.18 times negative, and we're going to go ahead and divide by 1,000 just because we're going to put it in kilojoules. You can leave it in joules. -9.4 0.41 kilojoules. Okay, so we got a negative number. That's what we hope to get. All right, and I'm going to circle this so we can come back and find it easily. All right, so now we're going to do part two. Part two, there is no temperature change, which means we're going to have to use a constant. So for this, we're going to use delta H of fusion, except for we're going to have to make it negative. So we have 25 grams times the intrinsic property, but it's negative 335 joules per 1 gram. Grams cancels out. Put it into the calculator. And if you want this in kilojoules, you will then divide by 1,000 and get negative 8.38. That's an 8 kilojoules. All right, we can't stop there. We have to keep going. So for segment number 3, we also have a temperature change. So we also can Q equals MCAT. Q equals, our mass is still 25 because we still have the same amount of substance. We have to be careful here because we have to use the specific heat of solid water, which is ice. And when we do the temperature change, so in this case, again, we're only doing the temperature change for this segment. So the final temperature is negative 10, and we started this segment at 0. So it's not all the way back up to this 90 because we already took care of that up here. We're only doing this segment. So 25 times 2.6, and we're going to divide by 1,000, so we get 0.515. It's negative kilojoules. And so to get the overall value, we are going to add all of these values together, and they all are negative. Oops. And we get negative 55.9 kilojoules. Not kilojoules per mole, but kilojoules as our overall problem. There are a lot of great practice problems on the practice sheets and the review on this, and ones that aren't going to be for water. And so you can practice some of those. Thank you for listening.